kind of get going because we have an hour. I think this is going to be a rather intriguing both presentation but conversation. And Kevin, as you've seen the bio, but I've asked him to give a little bit more as the executive director of the Geospatial Innovations Facility, which is fascinating as the name itself, at UC Berkeley. And this all started when Kevin and I were both presenting at a conference on climate change that Northrop Grumman, a major corporation, held in Southern California last spring, which I found fascinating itself, that they would, there was a reason, by the way, but they were taking the lead in California's climate change strategy planning. But that's another story. But anyway, Kevin was rolling out the beta of this CalAdapt, and I was flabbergasted because it looked to me at the time like it was going to help people imagine, see, visualize the multiple effects of climate change coming out of a decade of scientific assessment of those impacts. And every audience I had been to up to that point in classrooms since, I don't know anybody who's read any of those peer reports but me. And I'm not alone. You're not in my class, though.
Oh, okay.
I'm talking about the public presentations I've been at. And what it tells us is that science information, as valuable as it is hidden from public view. And yet California as a state has put together an incredible amount of information. So now comes along Kevin and says, let's make that accessible and visible, and all the issues that entails in doing it through GIS. Now I'm going to turn it over to you. So take it away.
Thank you very much. I will say, just with that great introduction, that this was not my brainchild, but we actually responded to a call that the CEC wanted to do this. So the
CEC is the
California Energy Commission. So they do get some kudos for really wanting to engage the public more with this information. And so thanks very much. I'm really thrilled to be here. And my first time visiting USC. It's a really beautiful campus. And I've been in California for only 3 years now, up at UC Berkeley, and an East Coaster all before that. Just to give you a little bit of background, I really got started as a biologist, a field biologist, and worked as an intern for the Smithsonian, has a conservation research station out in a place called Front Royal, Virginia, and we would do species radio tracking and things like that. And so wintertime, I got in the GIS lab because it's cold, and really took to the computers there and started working on endangered species monitoring and deforestation with satellite image analysis, and went on to work at the Natural History Museum, the American Natural History Museum in New York, and continued that kind of conservation work, mostly in Southeast Asia. So I did a lot of work in Myanmar, Laos, and Vietnam. And then 3 years ago, responded to this job opening at UC Berkeley to work with the GIF facility there. And it's been a really great experience. And I've been able to take everything that I've learned using GIS and geospatial a step beyond the conservation realm to really serve all of our campus and community beyond. So it's really great. We get to work with a lot of different people from a lot of different interests. And I find that many of the same techniques and methods and things that you use for one application really can be carried across to many different fields. So before I begin, too, I'd like to point out that there's been many people involved in this project. I managed the CalAdapt project itself, but Brian Gailey and Sarah Van Wart are two developers, so all of the magic you're seeing that happens on the server side and on the user interface, they've been really done an amazing job. And we recently had Matea Marsic join us, and she's developing some new tools. And Mark O'Connor's our IT support, and Maggie Kelly's actually our faculty director of the Geospatial Innovation Facility. And so just a little bit about the GIF. We support geospatial and promote geospatial technology on campus. And so we have a research space where students, staff, and faculty can use the software and use the hardware to enhance their own research with GIS and remote sensing. And we have advising, support, workshops, et cetera, to help this along. But we also have our own staff that is involved in our own research projects. And so this is coming from that side of things. And the lab itself was developed in 2005 and grew out of remote sensing being part of the College of Natural Resources. A lot of forestry folks were using remote sensing, and has really grown, though, and trying to keep up with where geospatial is heading now, we've been doing a lot more webGIS, and that's really one of the areas I think that has really opened up the whole world of geospatial to not just a few scientists, but to really everyone. And so anyone with a cell phone now or smartphone and anyone with access to a web browser is using GIS on a daily basis to get their directions and to do different things. And so I'm really interested in making that kind of visualization possible for a broader audience and taking what traditionally would be held by a few to be visible to many. So a lot of our work is going in that direction. So this project, CalAdapt, is on behalf of the California Energy Commission, and they have a program called PEER, the Public Interest Energy Research Program. And as Dan was saying, there's been a decade or more of work, and they've produced more than 150 peer-reviewed reports on climate change and the state of California. And you can go to their website and download any of these PDFs. And it's really amazing. There's been researchers all around the state. Is anybody here you have been funded by PEER for climate change projects? Often, I'm surprised there are many. So
kept to the UC.
Is that right? So the research has been broad and looking at lots of different topics, and these reports are a great resource. But a byproduct of all that resource is the data that's been developed in order to do the analyses. And so up till relatively recently, vast amounts of data that have been developed only existed available to a few people on a hard drive or an FTP site that's privately, you need a login to get into or something. So our mission was to develop an innovative web-based platform to increase access to the wealth of climate change research and data that's being produced within the state and the scientific community. And so there was a lot of considerations that we had to consider to do this. How we wanted to do this was to provide a relevant information presented in easy to understand themes and topics. We're very interested in geospatial, obviously. We're a geospatial facility, and with climate change, everything is happening in a place, so maps are a really great resource to provide visualization to a lot of the different topics. So having interactive maps and charts to help people explore different aspects of climate change was something that we wanted to provide. And then also improved access just to the primary climate change data in GIS and tabular formats, because like I said, even though the data was there and other experts might be able to use it, it was kind of locked away in different areas. So that leads us to the audiences that we're trying to reach with CalAdapt. And this is one of the primary challenges in developing a compelling site that many people could find useful, is that we have lots of different kinds of people. It's on the web, anyone can look at it. So we need a little something for the general public who may be stumbling upon the website for the first time and really just learning what climate change research is saying about their state. Local planners and technicians have been a large focus. So with the reports, you might get a chart or a map or a graphic showing you the entire state and what the projections say about climate change for the state. But if you're in the desert or the coast or the mountains, these changes could be very different. And so we really wanted to be able to create a localized application so that folks who need these data to do their jobs have better access to it in a lot of different ways. Not everybody's a GIS user, so having easy-to-use web maps that they could access the data is also important. But then we also have the scientific community who wants access to the data in a variety of formats. So not only do we have several of us working in the GIF on this, but this is really a collaborative effort from many institutions. Our advisory oversight from the CEC, they're definitely engaged, and Natural Resources Agency, we work with them a lot, and they're very interested in highlighting different data sets and coming up with different things that are of interest. And Google.org has also been on our advisory staff to help in visualizing and coming up with technical things. But all of the data that you'll see in the site have been provided by different research institutions that have been doing peer research. And so the data sets that are currently live on the site now are derived from research from all of these institutions here. But there's actually many more, and so as we continue to add data, that list will grow. So we had about 9 months to develop the site before launching publicly, and it went through several iterations of changes and testing in order to come up with what we have today. So one of the things we did while we got started was to find potential users from each of those different audiences and pull them and use surveys and interviews to try to better understand what they might need, why would they use the site, what can they get out of it. And so that was really helpful, and we had I would say, a dozen people that we would work relatively closely with that we could speak to and test and run different things by. But then we had about 100 beta testers that we would be able to survey online and come up with things that way as well. So we had an initial beta release privately, and we had a few iterations where we were able to get good feedback and continue to develop the site. And by no means is everything that we want to happen on the site complete. There's plenty more that we can do and are continuing to do now. But a big thing also is the accuracy of the data and the interactive maps. So we also had to work very closely with the scientists, not only in getting their data in some sort of format that we could use, and there's not always a direct correlation between the formats that climatologists use and the formats that GIS users use. So we had definitely some challenges just to get everything jiving together. But then also, we need to make sure that the data is being presented in a way that they're comfortable with, and their name is down there, that it's their institution's data. And so we would, before any tool gets launched to the public, it's verified by the authors of the data. So the majority of the data that we're providing right now come from the IPCC's downscaled climate projection model data. Just glancing at this slide, can I get a show of hands of people who this doesn't look foreign to? Does this look familiar to you? Okay, so I'm going to run through this a little bit. So the way the data comes from IPCC is they have different scenarios that are based on different socioeconomic population projections, lots of different things that may occur in the future that they're going to base the then climate projection models on. So because nobody knows exactly what is going to happen, we have several different paths that these things can take. So the A2 would be the medium-high emissions scenario. It's not the highest emission scenario, but pretty high. And the B1 would be lower emission scenario. So among these two, most of the rest kind of fit somewhere in between. But then there's also different centers around the globe that have run these global climate models. And so we have 4 of those that we have the data access to. So NCAR, CCSM, GFDL, CNRM, and there are many other labs around the world that have produced. These are the 4 that we happen to have. And the data sets that they provide are on a global basis, so they're very coarse. California has about 5 grid cells for the state, so it's really meant to be looked at on a global level. And what Scripps at UC San Diego does is downscale that data to a higher resolution using different sorts of climatological techniques that take into account ocean currents and terrain and lots of different factors. And so what they've done is they've taken those really coarse data, and for the footprint that we have around California, which actually also encompasses Nevada, some of Oregon, some of Arizona, they provide all of these different data layers that you see on the right that are modeled from 1950 through 2099. So the different data sets that I've highlighted in bold are the ones that we have web maps now available that you can go and look at these data sets within an interactive online environment. But if you are interested in any of these others, there's also in our data download section, all of these data sets are available for the raw data to be downloaded. But this is really where the challenge comes in. You know, I don't know how many of you are GIS folks, but the data side is extremely heavy and kind of unusual for web mapping. So web maps have gotten very good at being able to find a point or a polygon or a line. You can click it, you can get some information about that. But we're dealing with large amounts of time series raster data. And to have a good way to visualize that on the web is still kind of in its infancy. So Brian has done a tremendous job of trying out lots of different formats and languages and applications and things on the server side and client side to get this to work. And he would be the one to talk about more specifically, but he's using something called, in the Python structure, numpy arrays. But I guess the one thing I'll say is that all of CalAdapt is based on open source software. So none of this is actually using anything proprietary. It's all open and free, and anybody could use these tools to create something like this themselves. And so for each one of these data types, like maximum temperature, you have 150 years of data, 12 months for every year. It's monthly averages. We have 4 models I showed you for each of those, and 2 scenarios for each of those 4 models. So for any one of those topics, we have 14,400 layers to work with. A lot of data. And so that's really been a huge challenge. So what we came up with is this array structure called numpy arrays, where you could stack the raster data layers. So if you're unfamiliar with raster vector GIS terminology, rasters are essentially just grids of data cells. If you zoom in close enough on a digital camera photo, you'll see the pixel level, and that's a raster data set. So in this case, each grid cell represents temperature, if we're using temperature here, for a given month in a given year in a given model scenario. So we have these thousands of raster layers. And that's the one good thing I'll say about this that makes life a little easier, is that there is consistency, because all of these data layers were created by the same lab and the same process. They all match pixels exactly. So once you start bringing in other labs' types of data, then it gets even messier because there's different resolutions and things like that.
And how big is the resolution?
So in this case, we have 12-kilometer grid cells, which seems rather broad when you consider that you can see your car in Google Earth now and that sort of thing with 1 meter resolution. But for climate, it's very, very high. There are actually higher resolution data sets that have been developed just in the last year or two, and we're considering adding them to the site. But it's a whole nother level of
But is there data for each cell? Or is
Yes. Yeah, so for this case, we have data for every 12K grid cell. And so what we're able to do is when you click on the map or search an address or query the data, it instantly drills down to that grid cell, extracts all of the values, and enables us to rapidly produce it into interactive charts and tables and whatever you want. So in the tables and the charts that you see, basically every data point value on those is coming from a single raster layer. Sorry. And so with that, I figured I would show you a live demo. Hopefully everything's working well and quickly.
I wonder if it might be useful to lower some of the lights, maybe the lights right in front of the screen, just so that we get a cool.
Thanks. Yeah. And yeah, please interrupt me if you have any questions or comments as I go. The one thing, the mouse here is a little on a slope, so hopefully I'll work it well. All right, so it's cal-adapt.org, and it's open to the public as of July, so you can navigate to there. And so we did spend a good amount of time too just trying to create a friendly user interface, and this is what we've come up with. So this first tool here is the one that we developed mostly for the general public, kind of one-stop shop where you could get a little bit of information for your area and then dig a little deeper with the more robust climate tools that have more information. There's also resources like links to publications and things. Yes?
So the four models, where is this data coming from, this projection?
I'll show you, I'll talk more about that as I dive into the tools. And then the access to the primary data. And we're starting to build some community tools to try to engage the public further. But to start with, maybe I'll show you this page here. So this would be the currently available list of different climate tools. So the majority of them are showing things about temperature right now, but we also have snowpack, precipitation, sea level rise, and a wildfire risk map. And so if I start here with the temperature decadal averages map, what you're seeing is a map of the state, and we're currently set to the 1950 time step. And for these are sort of map animation, and what we've done to enable the transitions to move smoothly and be more meaningful, we're at a 10-year decadal average. So each time step you see as you slide the slider bar across is showing you what the average temperature for the state is projected to look like from 1950 through 2090 on a decadal average time step. And so what you'll see then is, very quickly you can take a look and get some information, but there's a lot more to it if you want it. Just to give you the lay of the land, most of the tools all kind of work very similarly, so once you've got the hang of it, it's relatively easy to jump around. But at the top here, you have some instructions that will walk you through different things you can do with the map. There's a little YouTube video tutorial as well. More information about the sources of the data. So where did the data come from, links to their labs, more information about the actual data set. And if there's any additional calculations that we did, like in this case, we did 10-year averages, we list that information there as well. And as you can see, there's a lot of terminology with climate change science that a lot of people might not be familiar with. So, all of these terms that we thought could use further explanation, we've created the ability to hover over and get a quick definition. So, like the models, for instance, you can see what does GFDL mean here by context. And then lastly up here, you can also share anything you're looking at in here. You could view it in Google Earth, download the primary data, download a JPEG or a PDF report. And And then over here, we have a dynamic URL. So if you're familiar with using Google Maps to get directions from one place to another and maybe emailing that directions to your friend, you can get a really long dynamic URL that when they paste in their browser the URL, they'll see exactly what you were looking at. And so the same is true here. We have, as I'll show you, we have lots of little different settings that you can adjust throughout the maps. But as you change those settings around, the URL will change. So if you find something really interesting you want to share with someone, you can just paste them that URL, and they'll be able to see exactly what you were seeing. And then, of course, you can also tweet and Facebook those things as well, if that is of interest. So, and this comes in part with the challenge, as we said, of having tools available to different audiences. So, we wanted to keep the interface as clean as possible, but there's a lot more information available that a lot more people might be interested in. So that's where the more options comes in. So right now, we're just looking at average annual temperature for the state. But let's say you want to look at the month of November instead of the average annual. We can see what does the November average temperature change look like, or July, and you can see that they're quite different. Another thing you can do is look at the different scenarios. So right now we're on the A2 high emission scenario, and if you choose this button here, the data will then load for the B1 low emission scenario, so you can compare the differences between these different scenarios. Also, I mentioned that we have 4 different scientific models to work with. And what you're currently seeing is an average of those 4. So usually when the scientists have access to many different models, they'll make an ensemble average of them to kind of filter out any particular outliers. So that's what you have here. But if you want to look at any individual model and compare those, you can also pull those up and see how do the different models perform. And lastly, in here, we're looking at average temperature, but we also have access to T-min, or temperature lows for the time period, or T-max, temperature highs. So we can look at those differences. And so for any of these areas as well, we're just looking at the entire state, but this is an interactive map. So I can zoom in and focus anywhere. I can search by address or click on the map. And so you'll see in orange, that's the pixel resolution that we're working with. I think it's a little slow on the individual model.
Is that slow because of our system or because of the way?
No, likely ours. But this is rare. There we go. Yeah. Once it clicks in. Also, I usually don't show it on Internet Explorer, which can sometimes be a little finicky. But the newest Internet Explorer seems to be much better.
You're sitting in the Los Angeles area where we sit right now.
Right.
Projected.
So for Los Angeles area, you can actually look at the chart for all of these given layers. And sorry, it's blinking, but from 1950 through 2090, here you can see what that data layer is showing you charted.
But if you want to just, for a second for me, so you can already go to 210 and show that the average temperature has been increasing.
Right.
Which I think many people don't even realize who live here now.
Right. And one thing, though, that's a good point that I want to mention is that all of the data we're looking at right now are modeled, though. So we're not looking at observed data from 2050 through present. So the climatologists use modeling, both hindcast and forecast, so that they're using a consistent data set throughout. And when they do degrees of change and comparisons, they tell us that that would be the the best way to go.
I don't understand, if I may. Are you saying that I looked at 2010 and the data report for 1950 is the retrospective modeling for that date?
Yes.
So is there any kind of check on its?
Yes, and I do have one chart that has observed data in there. And so this is one of the questions that has come up quite a bit. And so the climatologists are very interested in having the math and the change statistics derived from all model data, because essentially if there is any inconsistencies between the model data and the observed, you don't want that to actually then come out with different numbers. But this is something I can speak to what I've secondhand heard from them, but I will say I'm not the best to answer those actual modeling questions. We're responsible for the visualization.
But they're calibrating their models to
yes,
the observed.
Right. So the method they use to create these models is called bias-corrected statistical downscaling, BSBCSD, and that actually takes the observed data and calibrates their models to the observed positions. And so what this map shows you is degrees of change, like I was talking about. So the last map we were just looking at.
Not just degrees of change, but also change of degrees.
You'll have to excuse here.
Excuse me. So what you see is the fact that you're not having a consistent amount of change throughout the state. There's a lot of diversity, and so you may be able to see in a report or something a few statistics for a few cities or something about what's expected or projected to change. And what this map is showing you is the baseline period, which is 1961 through 1990, and subtracted by the end of century period, 2070 to 2090. And so what you see here is the red areas are up to 7.3 degrees Fahrenheit, whereas the yellow areas are at a 4.6 or 8. And again, you have more options here. So this is one where we're looking at the average annual temperature, and you could see the coastal areas are projecting less change than inland. If I look at individual months, like July, you see actually that the greatest amount of change in July is projected to occur in the northeast, while less so in the south. And then if you look at November, it's a different picture. So part of this is just having access to not only the data themselves, but greater temporal resolution hopefully would be able to inform folks who have an interest in growing seasons and different seasonal changes that might be happening. Yeah.
And if this question kind of throws you off track from where you want to go, please feel free to just push it back. But I make a distinction between spatial data models and spatial process models. And this seems to me like a very lovely example of an interface to spatial data models. And there are, of course, some implicit process models beneath that generated the data that are being interacted with here. But part of my reason for coming to this is I was sort of curious about what tools there may be that are kind of decision support tools and that's where it seems to me that looking at some spatial process models that couple with this could be useful. For example, a spatial process model of flooding. Right now I've got some friends and colleagues in Bangkok who are, we're writing back and forth, and they're trying to think about what kinds of, what can they do, right? And so I'm just wondering whether you all have begun to sort of open this up to spatial process models that that might couple with this that might really link to decision making?
Right. No, it's a great question, and definitely something that needs to be done. And we were just talking, so I think there's a lot of folks involved in this stuff, and we kind of each can play a different role. And rather than trying to kind of do everything, I really don't think we have the resources to answer all of these questions and create all these abilities. But organizations like ICLEI are providing great resources to do planning and answer those questions. And what CalAdapt does is provide that basic initial information that can then inform those later planning decisions.
And I'll just say that at ICLEI, we have struggled with adaptation in a way that we didn't with mitigation, because mitigation lends itself much more generally to decision support tools and models. We can refine them for California in input policy, but adaptation is much more micro-regionally specific, and we are working very hard to find some of that higher level guidance for local governments and decision support type things, but it's a much tougher nut to crack.
And I will also say that on our list of things that we're working on in the upcoming releases in the future are increasing the output data ability. So currently you can work with the data here on all the tools I'm showing you, and you can export the raw data. So if you're a scientist or GIS user or something, you can download those data and use them. But what we'd like to do is actually create more online data streams and feeds so that the data could then be fed into some of these additional tools that are being created by other institutions more easily, rather than everybody having to download and recreate everything from scratch. So moving on, the next tool I'll show you is also looking at temperature. And this one is actually showing you a lot more resolution in the chart. So what we're seeing here, and this is the one place where I mentioned we have observed data. So in blue here, you're seeing the observed temperature data for this particular grid cell. And so the temperature data here comes from Santa Clara University. There's a scientist, Ed Maurer, who's produced that data set. And it happens to be the data set that was used with the bias correcting and modeling that Scripps had done. Oh, right. So yeah, you can click around. And what you're seeing here is in blue, the actual observed temperatures. And then in 2000, the models kick in. And in this case, you get to see all 4 models at once displayed. And then the orange is the average of those 4 models. So you can see some show lower, some show higher. But then you do have the averages as well. And again, here, we can look at temperature lows. You can look at the temperature highs and get a better sense for everything that's happening or projected to happen. And as well here, you're looking at a line graph. You can look at a table. So each of the temperatures that you're seeing here is one of those raster layers that's been intersected to create that chart. And if you were interested in creating one of these for yourself, this is just visually, but if you want to download, there's access to the data in raster and tabular formats, which I mentioned. So I'll start with the raster downloads, where you can go in and select any of these particular data sets, the time step, the years that you would like to download, months, scenario models, and right now you can download them in either GeoTIFF or ASCII grid format, and it will bundle it into a zip file and deliver it to you. But that's just going to give you the raw GIS raster files. If you're an Excel user or want the data for different statistical applications, you can use this tabular downloads tool, where you can either select different points around the state, or here you can actually copy paste your lat longs into the window to select the grid cells. Select a data set, scenario, models, time interval, and when you download, it will deliver you a CSV file that shows you all of those data sets. And so this is something that we were doing in ArcGIS before I had our developers on it, and this operation, which I just did in a second or two, would run on ArcGIS for about 24 hours. So that's been really helpful. Another tool that you could check out would be looking at snowpack. Starting to slow down. Yeah. Let me see if I go in a different way.
It's melted.
I apologize.
Let's try some water.
Like I said, I usually don't use Internet Explorer. This
What
is
do you
rare.
use?
I use Firefox or Chrome. It works flawlessly. Yeah. I don't know if you've developed web applications before. Essentially, you have to develop like 2 different sets of code, one for everybody else and one for Internet Explorer, because they play by their own rules. So here's a sea level rise map, and this is showing you data for the California Bay Area, the San Francisco Bay Area, that was produced by USGS NOAA Knowles Lab, and the Pacific Institute also provided data then for the entire coast. And what the data is showing is, in this case, 100-year flood event projections. So if there were to be a large flood event, a 100-year flood event right now, the areas in blue are currently in threat of flooding. The areas in yellow are then additionally threatened given 1.4 meters sea level rise. All right. So I mentioned too that while we were developing and working with this, it's become apparent there's many great organizations doing work with sea level rise, and a lot of them have really great web resources up. The Pacific Institute is among them, and so rather than try to reproduce everything, we basically made this one tool where you can view their data, but I encourage you to look at their own tools because they're doing a lot of great stuff, and that's given us the ability to focus more on the temperature and other climate indicators that are less available in other places. Wow. And I also mentioned that we have this local climate snapshot tool, which is kind of the place to go for very quick and easy access to some basic information, where you can look at temperature and get the historic average, the low emission scenario at end of century, high emission scenario, and here you could see it plotted out, and the divergence between these different scenarios for that given area. For snowpack, you can click on a given grid cell and look at the projected changes in April snowpack, so the bellwether month for snowpack in the Sierra. Wildfire risk. This is a data set that was developed at UC Merced by Tony Westerling's lab and shows increased risk of wildfires given the climate change scenarios. This is one of the areas that's getting a lot of attention now, and so there's new data sets coming out. The original data sets were mostly just using temperature and rainfall and that sort of thing, but now they're looking at fuel and land cover, and all of these data sets are continuing to be refined. And that was something we were talking about earlier is, this is a field where things rapidly change, so how do we keep up with that? And one of the things that Peer wants to do is to make sure that before any data set gets put onto the site, it goes through some sort of peer review process so that it's not just any and everybody's data can go up there, but also that there is the ability to add new data sets as they become available. And so we're only now confronted with, very soon we'll have new IPCC layers coming out showing temperature and things. So do we replace all of the data with the new data, or do we have an updated area? And we're leaning towards having some sort of toggle to go between the two different data types, as there's probably going to be an interest in comparing. And the other thing is a lot of the reports that are coming out of Peer are based on these data sets that you're seeing here. So you want people to have the ability to see the original source.
Yeah, so if I could just ask an interpretive question on the right there, you're showing us that under the high emission scenario by 2050, the likelihood of a significant forest fire throughout the state in the northern part there is at least twice what it is today, 100% increase over today, and by the end of the century is up to 200% increase. Is that what you're talking about?
These data sets indicate.
Yes, that's what I'm saying. That's why I read that.
And this is the A2 scenario, and the darker one here would be the low emissions.
Yeah.
Yeah. And so I'll also mention that we're working on new tools, and in December hope to have a new set of tools up that are using the daily data. So everything you've seen thus far is looking at monthly averages, and there's a lot of interest. There was just a report out today on extreme events coming out of the IPCC, and so the daily data do a better job of describing how extreme events might be projected around the state. So we're currently working on a extreme heat event tool. I can show you an example of what that would look like. This is a chart that Dan Kahan's lab at Scripps had produced, showing number of extreme heat events for Los Angeles from the GFDL model A2 scenario. And what you see is the number of days that and this is May through September, number of days that the heat exceeds a certain threshold. So in this case, any day exceeding 81 degrees, which is the 95th percentile of daytime temperature from 1961 through 1990. And what you'll see is, as you move along, the projections show a large increase in the number of days expected to cross that threshold. So these have implications to public health and lots of different areas. And so, yeah, keep an eye out around mid-December for some new tools around those things.
Kevin, before you may have more, but I'm thinking also I'm watching the clock here. Maybe we could just stop for a second.
Yeah, no, I'm done, sir.
I thought it sounded like you were the last one, but open up to questions and comments.
Going back to the previous slide, the risk, I kind of interpret with that. So then 1.1, 1.2, those are what then?
Right, so the fire data is a bit of a different type of data, and this data set in particular is looking at the historic amount of fire in an area and then projects the increased number of times threat that you would have area burned. So the increase in area burned, yeah.
1.1 times, like 10%?
Right, increase in area burned. Yeah.
So below 1 is a decrease in that case? I mean, I don't see it here, but just hypothetically below 1 would be decrease.
Oh, and I can also mention briefly
And
about,
also,
But 2 is a doubling of the probability,
Going
right?
back to that,
right. Sorry.
you can go back to the fires chart again, the web fire, that table. So, why is it that in 2050, there's less chance of a high emission scenario?
I don't know that I'm qualified to answer that. It's very much dependent on that exact location that we're looking and what the projections
No, I mean,
are
everything
saying.
going up,
Yeah.
all of a sudden, why,
Right.
there would be a drop.
Yeah, I mean, I'm not sure. It's a mixture of what might happen in precipitation and snow and temperature.
And then a specific year, it's not
Yeah, well,
necessarily,
but a bit
the
of
temperatures are not growing linearly,
Right.
but in that specific year, there's gonna be more precipitation and more humidity.
Right, and these are looking at average time periods, not just one
But if you
year.
Tony, I've
Yeah.
been with Tony on this, he will tell you that it really is a combination of these factors. He sees this as exponentially growing after the mid-century. And he sees it because of the combination of the ground level management, that is the.
Which Tony?
Pardon me?
Which Tony?
Westerling, whose data is used
Okay,
here.
right.
And it really is the precipitation combination, plus with the die-off of trees and beetles and so forth, looking out over the life of the forest.
The
And-
biomass.
And the biomassing, and there are strategies he also has, by the way, for managing the forest so this doesn't occur. So someone asked about that, but it's not part of this.
The model includes that, the policy variable.
No, he doesn't. He says this is business as usual, what it will look like, goes into this data. If you want to say, if it's not business as usual, what do we need to do? And I'm just saying Tony also has strategies for management that go there too. It's just not shown this way in this particular portrayal.
I also just wanted to mention that we, hopefully by spring, will be launching some community-based tools to encourage more participation. One of the ideas we had was if anybody does geocaching, where you can use a GPS to go find some treasure that someone's left somewhere, there's actually a huge wealth of historic ground-level photos that USGS took as part of the Wieslander data set in the 1920s and 30s all around the state. And these have been digitized and are there, and they were labeled on a topo map where they were taken. So we have kind of the loose.
That was very far-sighted of someone.
Yeah, so we have the loose location. It's not GPS accurate, but general location of all these photos. And we'll invite people who are camera savvy and GPS savvy to go out and try to find these exact shots and replicate them today so that you could do before and after comparisons.
Student projects are going to go endless on that.
Yeah.
Yeah, right.
There's actually a really great, we got this idea, you can see down here a link, there was a master's student at San Francisco State who gave a talk in our lab who did this in Yellowstone, or not, in Yosemite. And his project you can find online and has some really great before and after shots that you can see how this has worked and watch where the tree line is and different aspects of the environment.
So you had said something to me that you did mention here, talk about last, which I wanted to bring up, and it was mentioned earlier, which is the concern of the climatologists and other natural science people about the certainty with which this may be taken, or the probabilities with which these projections are going to come to pass when viewed by the general public.
Right.
How do you cope with the fact that there are uncertainty boundaries around all this information that you are now compiling and showing
Definitely.
to the public?
Now, this is a struggle and a tough one to address. So, there's a lot of concern about understanding and conveying uncertainty, and the scientists are very interested in that their data is displayed in the right light, and that people understand that there is no certainty in 2090. We're not sure
So
what
the
this
answer
is
to
going to
this
look
question about how do you portray uncertainty is I'm not sure.
like. Not quite.
We're not sure, right? Yes.
No, I think that there are ways to portray it, but there's a balance between giving people indications of uncertainty and not just scaring them away to think, well, I don't need to consider this at all because it's not certain. So in this case, I err on the side of providing as much information as possible. And so seeing a chart where many things are present at once, you can see that there are some models showing lower thresholds, some models showing higher thresholds. There is this disclaimer on all of the tools so that people can read that these are not predictions of the future. They are projections based on certain assumptions.
Well, and the key thing is you can go back and you can look at if someone is really serious,
Right.
they can go back and look at the models that generated these, and they can develop their own models if they wish.
Absolutely. And in fact, if you go in and look at the actual publications that were derived from these data sets, they've done a lot of that, and they continue to. So the scientists themselves are obviously really
With the data
interested
set,
in this.
publications from which these data sets were derived.
Right. And additional ones that are testing them, yeah.
Other questions for Kevin?
So I you have a feedback section. I was curious some insights into what type of feedback you're receiving from what types of people are using this, and how they're responding via your website.
Yeah, thanks. Yeah, so all feedback is great, and it definitely helps us guide what is important to be addressed and not addressed in our development. We only have a few of us to work on this. One of the things that we've heard a lot of, especially from local county governments and city governments in California, is an interest to have their boundaries present and being able to click on my county and get some statistics for my county rather than the pixel level. So that's something we're actually working on right now and going to address. But just in terms of the geography, it's a tricky question again, because if you're in a county that is half of it's in the Central Valley and half of it's in the mountains, those average values aren't really effective because the temperatures are so different in each area. So we want to use mins and maxes and different standard deviation to try to help people to understand that you can't just blanket these, and this is true for many spatial applications, not just this. But we will be building that in, and then also the ability eventually to draw your own polygons and get those statistics for areas of interest in that regard.
Is there any component of these models that deal with urban areas? Particularly, for example, this heat island effect that some of us worry about, right? It seems to me that in some of the mapping, you could probably sort of go to the urban areas and see how whether the urban areas are changing, the predicted change in their the temperature rise is higher than the non-urban areas or something like that. Can that be sorted out from this, do you think?
Again, I don't know if I'm the right person to ask. I think there's someone in the room who's better able to answer that.
The process that you're describing is called the urban heat island effect.
Yeah.
And that wouldn't be, in my opinion, the urban heat island signal wouldn't be embedded in these modeling scenarios. Because this is primarily looking at global climate models.
It's coming from, right.
That's correct. But then you could, I'm sure there's a way to integrate the urban signal.
But
with,
to the extent there is a socioeconomic component of this modeling, I understand, right? All of these models are taking into account some aspect of human ecology, human behavior.
They are, but it's a global anthropogenic change as opposed to the spatially specific urban signal.
Yeah, but the models are picking up temperature as it is. So they're incorporating it in a sense. It's a real issue. Yeah,
Right.
we should talk about it. Right.
Well, yeah, I want to sort of indirect it there. There's a way of
Well, Kevin was explaining that people are interested in the political boundaries, and so it's a broader issue as to whether you can incorporate census data, census tracts or
Right.
zip codes or anything like
Yeah,
that.
exactly. Yeah.
And that would give us a sense of the urban areas,
We've got
right?
population concentration.
Yeah,
The
exactly.
human population is part of this thing, so there must be taken account of the fact, the distribution of population.
Right.
Even globally, right? So that means which the urbanization and all of that has to be
And this
somehow
is
built into this thing. I don't know.
right. Well, this is exactly why I'm interested in having output data feeds, as I was mentioning, because there's so many questions you can ask that it's really impossible to make one tool that can do it all. But if you create a standardized format that others can ingest, then if you have a good source of census data, if you have a good source of other types of information, you can mash up all of these different data sources to do different types of analyses. There's actually a great example in San Francisco. I believe it's datasf.org or sfdata.org, one or the other, where the city of San Francisco had a lot of data and they realized they weren't utilizing it to its full potential. And they basically created a web portal that has these kind of data feeds for crimes, trash, you name it, city data, and have opened it to the public and allow people to develop apps on their phones and computer programs and things. And they have a gallery of what's come in just a year or two, and it's amazing. There's literally dozens of really useful apps that people are all using that are real-time fed with this kind of information. So I think the future of webGIS is yes, you want a curated environment for people to learn and understand, but you then want to shepherd people to a place where they could then combine those things with other sources.
From the urban planning point of view, I mean, future urbanization, the form of urbanization, whether it's a concentrated or distributed sprawl, and those are important policy issues that we deal with. And obviously, assumption has been that one type of urban form would create less emission or less global warming effect than the other. I mean, or other words, the footprints will be different and all that. So I think it'll be interesting, but to the extent we could build into this model those kinds of dimensions, the urban.
And there are actually urban growth projections that have been developed at UC Davis that we are yet to incorporate into this, but they have some data sets that are public. You can read the reports in Peer that show a lot of interesting things, and they look at different scenarios. What if this happens and that happens? What will the California population look like? Yeah.
Wow. Well, time's up, but we'll stay a couple of minutes if individuals have questions.
Definitely.
We tell you we'd be through by 1, but thank you very much, Kevin.
Thank you.